Hello, here's page 6 of complex numbers and polynomials. First, we're going to look through the page 181 properties of complex conjugates. Let's look at the first one. The conjugate of a conjugate is, so let's take a look at that. If I had like 3 plus 4i and I found the conjugate of that, it would be 3 minus 4i. And then if I found the conjugate of that, it would be 3 plus 4i, and I'm back to what I started out with. So the conjugate of a conjugate is equal to the original number. Okay, next one. The conjugate of two numbers added together, two complex numbers added together, is equal to the conjugate of the first one plus the conjugate of the second one. And how do we know that? Let's see. If I have 1 plus 2i plus 3 plus 4i, and I'm going to add them all together, and I take the conjugate, then that would be 1 plus 3 minus 2 plus 4i, okay? Which, if I just add them together without the conjugate, it would be 1 plus 3 plus 2 plus 4i. So the adding the two together would just look like this. Adding the two together and taking the conjugate would look like this. Now what if I took the conjugate of each one separately? So that would be 1 minus 2i plus 3 minus 4i. That would give me 1 plus 3 minus 2 plus 4i. And there we are. Same thing. So you can take the conjugate first and then add them, or you can add them together and then take the conjugate. Either way, doesn't matter. Okay. Same thing with subtracting. Subtracting, you could take the conjugate first of each one and subtract, or you could subtract them and then take the conjugate. Either order. Z1 times Z2, take the conjugate of the whole thing. That's the same thing as Z1 conjugate times Z2 conjugate. Let's see if we can figure that one out. So if we have 1 plus 2i times 3 plus 4i, and we want to take the conjugate of the whole thing, so we'll have we'll do FOIL. 1 times 3 plus 2 times 4 minus, right? Because this is a I squared, right? And then the imaginary parts would be 2 times 3i plus 1 times 4i, right? And if I was to take the conjugate of this, I would be changing these pluses to minuses. Okay. What if I took the conjugates of the inside numbers first? So I do 1 minus 2i times 3 minus 4i. Then I would have 1 times 3, negative 2 times negative 4 is positive 2 times 4, I squared is negative. That would be the other real part. And then the imaginary parts would be negative 2 times 3i and negative 1 times 4i. And if I look at this, it comes out exactly the same, doesn't it? Oh, I'm sorry, it looks exactly the same once I take the conjugate of this. So yeah, makes sense for that to be true. When you do a division, similarly, it's going to be the conjugate of the top number divided by the conjugate of the bottom number. You can take the conjugate first of the numbers, or you can do the division and then take the conjugate of the result. And of course, the bottom number cannot be 0. For this one here, if I multiply z times itself many times and then take the conjugate, it's the same as taking z conjugate and multiplying that times itself many times. Okay, so it's kind of like this rule here, except I'm extending it for like multiple z multiplications. Okay, last one is z plus z star and z star are real numbers. Okay, and we're familiar with this one, right? When you have z star, we know that when you multiply together z star, a number times its conjugate, that's a really good way of making the result real. We always do that when we see a real complex number in the denominator. We multiply the denominator by the complex conjugate. We multiply the numerator by the complex conjugate. Now, I don't think we've looked at that yet, right? But like if you take a number and its complex conjugate and you add them together, of course, the imaginary parts, one which is plus and the other one which is minus, will cancel each other out, right? Okay, let's move on to problem number 1. Try to use these rules to solve problems. Show that z1 minus z2 conjugate equals z1 conjugate minus z2 conjugate for all complex numbers z1 and z2. So usually when you get a proof like this, what you want to do is you want to name z1, z2 by their real and imaginary components. So like for z1, let's call it a1 plus b1i. That'll be a z1. And then we'll subtract a2 plus b2i, which will be z2. And then we'll take the conjugate of the whole thing. And then let's see. So that'll be, let's combine the real parts and the imaginary parts here. So I have a1 minus a2 plus b1 minus b2i. And then we're going to take the conjugate of this. So when we take the conjugate, we'll just do a minus here, right? And then we're going to compare that to the right side. So the conjugate of z1 is going to be a1 minus b1i. And we subtract z2, which is a2. That's the conjugate of z2, so it'd be a2 minus b2i. And then we'll do a1 minus a2 for the real part. And then we will do b2 minus b1, the imaginary part. And if you compare these two, this is equal to this. This, if you manipulate a little bit, is the same as this. Like, for example, negative b1 minus b2 is the same as positive b2 minus b1, right? So we've shown that both are equal, and we're fine. Okay. Number 3. It is known that a complex number z satisfies the equation z star equals negative z. Show that z is either purely imaginary or 0. Okay. So if you have a complex number z star, that's we could rename it a plus bi star. And then we will find the complex conjugate of a plus bi. It'll be a minus bi. Now it says that that's equal to negative z. Remember that z is a plus bi. So negative z is negative a minus bi. Now we know that this is the real part and this is the imaginary part of these complex numbers. Since they're equal, we know that a is equal to negative a, and we know that negative b equals negative b. Well, this is always true, of course, but when is a equal to negative a? Let's see, we'll add a to both sides. We'll get 2a on the left and we'll get 0 on the right. So a is equal to 0. So basically, the real part of the complex number is 0. So that means imaginary, right? And the only other possibility, purely imaginary, right? Because the a equals 0. But in addition to be purely imaginary, the b could also be 0, right? So b could be any real number. A has to be 0, okay? So it could be purely imaginary or 0. 5a. An easier way of proving this is to start with this. Okay. All right. So basically, if we start with this, you can see that this is kind of like one part of it, right? That part of it. So let's start with this relationship here. Z1 divided by Z2 conjugate times Z2 conjugate. We'll see what that is equal to. So, and we're supposed to use the fact that we already know that the conjugate of a product is the product of the conjugates. So, since we have a conjugate times a conjugate here, we could say that it's the same thing as Z1 divided by Z2 times Z2. We'll like unconjugate them, and then we'll make that we'll put the conjugate on the outside of the parentheses. And if we see that, then we know that Z1 divided by Z2 times Z1 divided by Z2 times Z2, the Z2's cancel out, right? So then we're left with Z1 conjugate. Okay? Now we can go back to this, and we could say, okay, here we have Z1, Z2 conjugate equals Z1 conjugate divided by Z2 conjugate. What if we multiply both sides by Z2 conjugate? Then we get Z1 divided by Z2 conjugate times Z2 conjugate. And on the other side, we're going to have what's the remaining on the right side, which would be Z1 conjugate. Once we have that, we have the relationship that we showed at the beginning, which we know is true. Okay, so basically we've taken the original expression and we've converted it into this expression, which we know is true. So we know we've proven it. Okay, B. So B1. Let Z equals A plus BI. Let A equals B plus BI be a complex number. Prove the following. If Z equals Z star, then Z is real. Okay. So if, let's call Z equals A plus BI. So we'll say A plus BI on the left of the equal sign. Z star is A minus BI. If this is true, then that means that the real parts and the complex parts are equal. So A equals A and B equals negative B. When does B equal negative B? Add B to both sides, you get 2B equals 0. So when B equals 0, if B equals 0, then that means Z is real, right? Okay, let's look at B2. So if Z star equals negative Z, then Z is purely imaginary or 0. So let's check that out. So Z star would be A minus BI, and negative Z is negative A minus BI. Now we equate the real parts and the imaginary parts. So A equals negative A and negative B equals negative B. So this is always true. And then A equals negative A is 2A equals 0. So A equals 0. So that means purely imaginary or 0, right? When A equals 0, Z purely imaginary or 0. Okay, that was 5. That's the end of the page.